there's some limitations as to what features that are actually supported in that particular network topology. Okay, additionally, implement IPsec with pre-shared keys. This is going to be a pretty straightforward and a pretty small scope of RNS. So for IPsec, it's definitely not going to be as large as CCI security. We'll talk about IPsec from a high-level overview. How does the Phase 1 ISACAMP negotiation work? How does Phase 2 IPsec negotiation work? But from a configuration point of view, we're basically looking at the easiest possible implementation of IPsec, where we're defining a Phase 1 ISACAMP profile, we're doing pre-shared keys, and then we're using crypto IPsec profiles in order to apply them to our DMVPN tunnels or to apply them to our GRE tunnels. So we're not going to get into things like dynamic crypto maps or AnyConnect VPN, Easy VPN. That stuff is still going to be outside of RNS and into the scope of security. So we're mainly looking at IPsec just from the infrastructure point of view, just establishing the basic tunnels that we can ultimately do routing over. We then have implement and troubleshoot IPv6 first hop security, which in the previous version of the exam, we already had IPv4 first hop security, which is dealt with things like dynamic ARP inspection, the DHCP snooping, and IP source guard, where there's equivalents in the IPv6 world. There's just some minor differences of how the actual operation works, and then of course how the configuration works. So we'll look at that when we get to the security section, but it's not really a huge topic. Now, in terms of topics that were added to the lab exam, so up to this point we're talking about just the written exam. Some of these we'll see do overlap, like using troubleshooting tools, applying troubleshooting methodology. Again, that's kind of self-explanatory because we know that troubleshooting is involved in the exam. There's a separate troubleshooting section, so of course you have to use troubleshooting tools. It's just that now it's a little bit more clearly spelled out in the blueprint what is specifically now in the scope. So again, interpreting packet capture, you're not going to have to actually create the captures or use Wireshark. They're probably just going to give you screenshots of this is the packet flow. Can you deduce the problem from it? Okay, then we have BFD, EIGRP, and named mode. Both of these are then on the written and the lab exam. Same with EIGRP, OSPF scalability, and then DMVPN, IPsec, first hop security, IPv6 first hop security. So these ones are both in the written and the lab. So kind of in summary, the big ones that are in the written and not in the lab would be ISIS routing, Get VPN for group encrypted transport, and then the layer 2 MPLS tunnels. So Ethernet virtual circuits, virtual private LAN services, those are going to be just in theory in the written exam, not in the actual implementation in the lab portion. So this is stuff that was added, but what about stuff that was removed? Okay, some topics were moved from the lab to the written, so they weren't removed completely, but they're no longer going to be tested from the practical configuration point of view. So specifically, these are IPv6 multicast, RIP version 6, or RIP next generation, RIP-NG, IPv6 tunneling, which I'm assuming is going to be talking about things like ISATAP tunnels, automatic 6-to-4 tunnels, because we are still going to be doing IPv6 tunneling over IPv4 in terms of running like OSPF v3 over an IPsec tunnel, or running EIGRP-v6 over DMVPN. So some of these we will still talk about in class. Whether they're actually going to test on them or not, we don't really know, but you're better safe than sorry. You're better learning how they work, and then if it's not tested on, then it's fine. It's not a huge topic domain that we really should skip over it anyways. Additionally, describe iOS AAA with TACACS and Radius. So this means that they're not going to be doing things like local command authorization, local accounting, remote accounting with either TACACS or Radius. This stuff is going to be reserved for the security exam. Okay, same with 802.1x, because now .1x is a very large topic domain when we're dealing with things like network admission control and the identity services engine. So .1x is now reserved for the security exam, but they could ask you just what is .1x, why would you want to use it? Another big one is layer 2 QoS. And the reason why this is removed is they're trying to make the exam more platform independent now. Now, if you're familiar with any of the layer 2 QoS implementations, essentially every single platform that they have has a different implementation of Layer 2 QoS. Because it's implemented in the hardware ASICs, it's not the same as doing general software queuing with the modular quality of service on the regular iOS CLI. So this means that if you had a QoS config on a 3750X and you wanted to port this over to a Catalyst 6800, well, you would need to know what's the exact line card on the 6800, how many priority queues does it have, how many drop thresholds does it have, and it gets very complicated in order to actually look at these differences. So where this would really be tested within the scope of CCIE is going to be in the collaboration exam. So collaboration does assume that you're doing very low-level details on Layer 2 QoS. And if you do want more information on this, when we get to QoS, I'll talk about what are some of the resources that you could look into. Mainly what is the Enterprise QoS, the SRND, the Solution Reference Network Design Guide. Then we have everybody's favorite topic from V4, which is performance routing, or PFR. So PFR is no longer in the lab. It is still in the written exam, so you do need to know just in general what is the feature set and what could you do with it, but it's not going to be tested on anymore. Now, in terms of topics that have been completely removed, both from the lab and the written, the biggest one, of course, is going to be frame relay. So frame relay is out, DMVPN is now in, but we'll see from a protocol design point of view, they're both going to be very similar to each other. The only difference is that DMVPN is an IP tunnel, where frame relay is a Layer 2 tunnel. But we'll see that the topologies that they form and the behaviors of the Layer 3 routing protocols over them are very similar. So again, if you know how frame relay works, that's not going to be completely useless information. A lot of that is still going to carry over into the Layer 3 routing over DMVPN. Some of the legacy stuff in Layer 2 Ethernet is removed, like nobody uses ISL trunking anymore. Everybody uses .1Q trunking. WCCP is definitely still a relevant protocol, but this is going to be moved to the security exam to be used for things like the web security appliance, the IronPort web proxy, where you use WCCP to capture the traffic and then redirect it. That's not something that's necessarily within our RNS scope, so that's out. That's now just on the security blueprint. Same is true with iOS Firewall and iOS IPS. This feature continues to get more complicated, so it's not something that is trivial to implement. So iOS Firewall is out. We're assuming this means both content-based access control and zone-based policy firewall. So either the IP inspect or the policy map, class map type inspects, those are now reserved just for security, no longer for RNS. Some other minor features like router IP traffic export or remote monitoring. With write, we don't really need to do this anymore because we have embedded packet capture. RGMP is legacy for multicast. Most people didn't even know that was in the scope to begin with. And then also some other variations of Layer 2 QoS, like weighted round robin, shape round robin. Since the hardware doesn't support this anymore, then there's no reason to test it in the exam. Now, in terms of the topology changes, specifically what the official CCIE blueprint says is that the configuration portion, just like troubleshooting was in the past, is now both on virtual routers and on virtual switches. Excuse me. What the big implication of this is that the topology in the exam is generally going to be very large. So I would assume that there's going to be 20 routers or more, both in the troubleshooting section and in the configuration section. Now, really, at the end of the day, though, it doesn't matter how many routers there are because the topic scope is still the same when we had the old topology of 5 routers plus 4 switches versus the new one that's virtual. The main difference this means is just that they can spread out the topics over more devices, and it's going to make the network have less interaction with itself. So their original goal of doing this in troubleshooting is that if I want to ask you 5 different troubleshooting questions, I don't want ticket 1 to have to relate directly to ticket 2 and 3 and 4. So they're trying to make the topology big so that the questions can be independent from each other. So even though the topology is going to be larger than it has been in the past, it doesn't necessarily mean that the exam is going to take you 20 hours to configure. So it should still be the same length of content. It's just that now the content is spread over more devices, and also that we're testing on non-hardware specific platforms. So again, things like Layer 2 QoS, very hardware specific, so they don't want to test on that anymore. Now for their hardware specs specifically, they're saying that if you wanted to use hardware to practice for the exam, you want something equivalent of 15.3T for the ISR G2s, or something equivalent to 15.0 SE for the Catalyst X series, like 3560X, 3750X. Okay, but the other key thing that they try to reiterate here is that it doesn't really matter what hardware platform you use, because the test is not hardware dependent. The test is basically now software dependent. So as long as you have a platform that can support most of the feature sets, then stick with that, and then you can use rec rentals or you can use other resources in order to get the remaining portions of it. Now, of course, we are going to be hosting the hardware topology, and we do host the hardware topology now. You can rent it right now, today, if you want. But you don't need to have support for every single feature at any given time, because you'll see the exam scope is so large. You might see that, you know, if I buy a regular Catalyst 3560 and then I compare this to a 3560X, what's really the difference between our scope? Probably 1%, 2% literally. So you don't necessarily need to go out and spend $100,000 in routers and licensing in order to practice for this exam. We're going to talk about here specifically what are the feasible platforms that you could use in order to build this topology. But let's say, for example, you work for a reseller and you already have access to tons of boxes, then use ISR G2s, use Catalyst X series, X or E, either one would be fine. Now specifically for our topology, in the V4 topology we had 6 routers and we had 4 switches, and then we had some backbone routers to introduce IP routes, like you would do BGP peering to a backbone router and then do some route manipulation, and then also the layer 2 frame relay switch that was building the virtual circuits between the devices. So the big limitation with this topology though, and this is ultimately why the CCIE program changed the topology, is that you're very limited as to the type of logical networks that you can build when you're depending on one specific set of wiring. So if you have 6 routers, it's going to be very difficult to build a large MPLS core that you're trying to route IP over. In the case of the new topology, us specifically, we're going to be using 20 virtual routers. So virtual routers, either you could run 15.4S, which is going to be the CSR 1000V release, or you could run 15.3T, which is going to be the IOU or the IOL release. So could be physical, could be virtual. We'll talk about this in more detail shortly. Okay, we also are going to be still using physical switches because the virtualization software still doesn't really support all of the switch features, but you'll see that the switching portion of the class and the switching portion of the workbook labs is going to be very, very minimal. So Ethernet is going to be tested on, but in the scheme of things, it's not something that's very complicated. It should not be an issue to form trunk links, to do access VLAN assignments, to do ether channel, to do spanning tree manipulation. There's a very limited scope as to what Ethernet on its own can do. Now, once the layer 2 topology is built, then of course all the layer 3 routing is going to ride on top of it. So it is important that layer 2 is properly built, but it should be something that you shouldn't fail the exam because of Ethernet. Okay, it is going to be in there, but it shouldn't be the most difficult portion of the exam. Now, from a logical point of view, what the topology now looks like is that there's essentially an interface from the physical world into the virtual world. So specifically with our topology, we have the physical switches. So switch 1 through switch 4, these are wired basically 2 links between each of the switches, so there's a full mesh of cables, and then there's 1 link that goes into the virtual world. Now, how specifically you build this is really up to you. You could also have all sorts of different options, and we're going to talk about them specifically here. What are those options? But at the end of the day, it really doesn't matter as long as you have software support that's fairly close to the topics that we're testing on. So if you have 2500 series routers with release 11.3, that's probably not going to work. But as long as you have anything that's probably 15.1T or greater, you're going to be able to do 90+% of the topics. But this is how our topology now works, that there's a physical link from the virtual world into the physical world, and then all the routers are connected to a virtual switch that is in the virtual world. So we'll see that when you do the configuration, if one of the tasks is not talking about layer 2 switching, you don't need to do any config on the switch. So you could basically just cut off this link, and in probably 80% or more of the examples that I'm going to be doing in class, we're not going to use the switches at all. So you can build the routers just as a virtual topology on their own, and then if you want to add the switches in later, you can, or you could rent time on our racks, which we already have the physical network built. Okay, this is also going to be true for some of the specific features that are in the 3560X or 3750X, where if you look at the price of those, if you're buying at retail, probably not the greatest idea. You could spend $100 in rack rentals and test all the topics in 2 or 3 days that you would need to use on those specific releases. Now, if you were to build the topology as physical, it would probably look something similar to this, where you have some sort of aggregation point for the physical boxes. So we have some sort of breakout switch, and you don't necessarily have to do this. You could take the routers and plug them in directly to switch 1 here. The only advantage of doing it this way is that if a task does not involve the rest of the switches, then you don't need to do anything with them. You would just go to this switch and basically say that all of these interfaces are .1Q trunks, and that all VLANs are allowed on all interfaces. So we'll see that when we're actually building the topologies and looking at the initial configs, the config of the routers is ultimately going to define what's the logical network. And there's a way that we'll see that it's very quick to switch between the configs. You'll see that on our rack rentals, it only takes about 20 seconds to change between initial configs. So you'll see that one of the changes that happened in the Advanced Technologies Labs, which is what we previously called the Volume 1 workbook, there's almost a separate initial config for pretty much every single task. But if you're using our rack rental system, it's not going to waste you any time. So it used to be because the boxes were physical, we had to reboot them, we had to possibly do password recovery, wait 5 minutes for them to power on, and then load the config. It doesn't work that way in the virtual world anymore. So if you click the button to move between configs, it's very, very fast, and you're not going to waste time on rack rentals switching between the initial configs. Okay, so let's talk about if you did want to build the topology, how can you do it virtually? Okay, us personally, we're running this on CSR 1000V. Okay, if you haven't heard of CSR 1000V, basically what it is the code base from ASR 1000, where ASR 1000 is the replacement for the 7200 VXR, which is Cisco's basically most popular edge router ever. So it's the enterprise edge router that basically has all possible features of iOS, but now it's compiled virtually. Now, the one key difference between CSR 1000V and the other solutions is that CSR 1000V is a production router. So it means it does forward in the data plane, and you're not going to run into features that aren't supported because it's running virtually. The only difference is that you don't have the hardware ASICs of the ASR1K in order to back up the CSR. So depending on your actual deployment, you might not have the throughput as you would the physical router, but you're going to have the same type of features that are supported. This is the main reason that we chose to go with the CSR versus going with the other virtual platforms, because if you're using IOU or IOL, if you're using GNS3, you will find that there's features that you configure correctly and they don't work, and then you have no idea where you're supposed to go in troubleshooting. So simply to divide the topics between, do I have a problem in config or is it a problem with the virtualization? You'll see that CSR 1000V generally is a much better solution for doing these type of lab scenarios. Now, within the scope of the exam, they're going to be using IOU and IOL, but the one thing to remember is that they're going to be qualifying every single question that they write in the exam against their individual release. Where when you're going through your general preparation, you're probably going to be going above and beyond what's covered in the exam, where in the exam, they're just looking at an individual snapshot of the technologies. So if you were to use IOU or IOL, you can do this, and it's a perfectly valid option. Another option would be to run the regular iOS code. for the 7200s. That's directly supported in GNS3 as it stands now. But if you choose this, I would highly recommend that you don't run CSR 1000V inside of GNS3 because it's not a very stable implementation. So if you want to build your own platform for running the virtual routers, you're going to be better off doing it as a dedicated build. So don't run it on your laptop, don't run it on your desktop PC, buy a specific dedicated machine and then run the virtualization on that. So if you choose to go with CSR 1000V, don't run it inside VirtualBox, don't run it inside VMware Player, it's not going to perform correctly. You want to run it on a bare metal hypervisor, either ESX or Xen or KVM. I wouldn't run it on Microsoft Hyper-V because there's some things that Hyper-V doesn't support. But otherwise, GNS3 is going to be a valid option. That would be good maybe like if you're traveling a lot and you don't have access to your physical build, then that would be a good solution. But the big issue, again, the difference between them is that not all features are going to be stable when you're running them in GNS3. So you might end up in these traffic black holes of wasting your time where it's really a problem with the virtualization, it's not a problem with the underlying IOS. Now, in terms of physical boxes, if you want 100% of the feature support, you're going to need ISR G2 or higher. So you could run all ASR 1000s if you have access to them, but the problem is that most people probably won't have access to the physical resources in order to do this. If you look at the pricing of these, the issue is not necessarily the price of the box, the issue is the price of the licensing. Because in the versions that we're using, the 15.3T Universal, you have to turn on the feature sets separately. So you basically have IP base, plus you have 3 additional licenses, which are base and then data and security. So data would be things for routing, like advanced BGP, advanced OSPF, and then security is going to be for things like DMVPN. So since our topic scope is so widely distributed, you can't get away with just IP base. You're not going to be able to configure any of the features. But again, if you already do have access to these boxes, that's a good solution because that is going to host 100% of the features. The other option is ISR G1. If you have 1800s, if you have 2800s, don't throw them out. There's still a lot of features that you can run on them. So officially, these boxes support up to 15.1T. If you're running these, the feature set you want to run is Advanced Enterprise Services. It's not going to support 100% of things, but it's going to be a really good start. So if you have this build already done, like for version 4, and you have these routers sitting around, then still use them and just take a note of what were you not able to configure that was on that particular release, and then rent rack time from us to do those features, or borrow somebody else's lab to do the features. So the point being, a lot of these core features are going to be supported in 12.0, because when we look at configuring OSPF, there's no difference between configuring OSPF 10 years ago versus today for the vast majority of features. Now, of course, once we get into advanced implementations like OSPF version 3, VRF Lite support for the IPv6 protocols, BFD support, LFA support, fast reroute support, that stuff is going to be only in the newer code. So you'll miss out on those features. Just write them down and then move to like rack rentals in order to support them. Now, of course, the other big problem with this, though, is that it takes a lot of space. It takes a lot of power and cooling in order to run these boxes. So if you have 20 physical routers, yeah, you can do it that way, but it might not be the best solution. Now, in terms of the switches, there's basically, I would say, probably two possible options for this. You could either run the 3560 or 3750E or X, but if you do this, you need the IP services feature set. So these switches run universal like the ISR G2s do. So in order to enable the features, you have to have the licensing for it. And generally, that's where the main expense is. It's not in the physical box, the expense is in the license. So if you are buying one of these, if you're buying it off eBay, for example, you need to make sure it has the feature set. Otherwise, you're going to be surprised when you get it. You go to type the commands in, and most of the stuff doesn't work. Now, in terms of the older switches, if you have regular 3560 or regular 3750, you can still run iOS 15, But there's one catch here. It has to be on the part numbers that have 32 megs of flash, and not all of them do. So, before we move on to this, let me actually show where you can find this. Is that if we go to, let me just search for this, which would be the Catalyst 3750 release notes. And actually, let me just search for the exact part number, which is under Catalyst 3560 data sheets. And here you see the exact part numbers. Down towards the bottom of this document, somewhere here, is here. So under the hardware, switch hardware, it says that they each have 128 megs of RAM. But if you look at the flash, not all of them have 32 megs. So specifically, 3560G 24TS, regular 3560 24TS, 48TS, and the 8-port 3560 actually has more memory than the regular 48-port PS. These are the ones that are PoE. So in general, the PoE versions of 3560 and 3750 won't run the 15 code. The non-PoE ones will. So if you want to buy switches to add to your topology, these are pretty cheap. You can probably get them for about 200 bucks or so, as compared to the 3750Xs, which would be like 2 or 3 grand, probably more with the licenses. So the key point being is that these do run 15. It's not going to support 100% of the features that the 3560 or 3750E or X does, but if you want physical switches, this would be a good choice. Now, you could, of course, use either layer 2 IOU or layer 2 IOL, but again, the issue really is going to be the feature stability. That it's better than it has been in the past, but you'll find that there are some strange caveats about what is supported, what is not supported. And the difference between how they're running that in the lab and how you're preparing is that when you're preparing, you're trying to test every single feature. When they're testing the lab, it's going to be a broad cross-section of the technologies, and they're only going to ask questions that actually work on their topology. So if they run into a bug, they're just going to move that to a different box or not test on that specific variation of the feature. But again, when you're preparing, it can be a very frustrating situation you run into where something's not working, you waste a bunch of time troubleshooting, and then you reload your GNS3 routers and you realize that that was the problem. Okay, with the CSR1000V, as far as I've seen so far, it's very, very stable, and there's nothing that I've thrown at it at all that has not been supported so far. Okay, so let's take some questions. There's a bunch of questions on this section. How about a mixture of real and virtual routers, 1800s and CSRs and EXX? That would be a perfect solution as well. So let's say you already have some routers from the previous topology, and your server hardware is not going to support a full build of all of the CSR instances, then there's nothing wrong with mixing them. So the only thing that you would need to do is just have some sort of interface from the physical world into the virtual world. So for example, let's say that you have, I don't know, maybe 6 physical routers. Router 1, 2, 3, 4, 5, 6. Just take these and plug them into a switch. Okay, this switch could be anything. Doesn't have to be 3560, whatever this is, and then just do a trunk on all of these interfaces. So that would be a trunk. And this would be a trunk. And then this goes to whatever your hypervisor is. So this could be ESX. It could be Zen, could be KVM. So whatever you're already familiar with, or I mean, this also could be GNS. So you can do an interface from the physical to the virtual world from any of these variations. So you could do all physical build, you can do all virtual build, or you can mix and match it however you want. The only real difference is going to be when you take our initial configs and load them, how much of a pain is it going to be to change those around? we've tried to make it a more cleaner, a little bit easier to manage than it has been in the past. So if you can just do like a bulk find and replace on all the files, and then replace them with whatever the naming convention is of your interfaces, then that would be a perfectly acceptable solution. Again, the only thing you need to do is just make sure that you take a note of what was not covered in your particular setup, and then just rent some rack time in order to do that. Now, if you actually look at our solution for this, and as of now, the version 5 control panel for our racks is not yet live. But let me show here just real quick how the rack rental system works. So when you go to schedule a session, and let's say I want to rent the session right now, you pretty much don't even need to schedule this in advance. You can just come to the page, and then it defaults to a 3-hour block, and it pretty much immediately assigns you that session. So let's see, once the page refreshes, it should say, so click on the control panel button here. And you'll see it says the other stuff is not yet published yet, but if I now telnet, and you guys are probably going to steal my password, you can log into this if you really want to. But if you telnet to racks.ind.com, here rs5 rack 6, RS5 rack 6. Oh, you know what? I think it didn't start yet. Did the session start yet? I should have checked the time zone on it. RS5 rack 6. There we go. And then if you open the boxes, this one may be booting. But the point being is that the access is basically immediate. You could book the session, go grab a cup of coffee, and by the time you come back, the initial configs are already loaded for you. So again, the control panel is probably going to be pushed into beta this week. And then as we work the rest of the bugs out for it, then it should be finalized pretty shortly. But you'll see that one of the big differences is that the load time for the initial configs is going to be much, much faster with the new system than it was in the previous one. So you can see by default with the current racks, you get 10 router instances and then 4 physical switches. This is going to go up to more boxes as we get into the other variations of the content. So I'll talk about that a little bit later today before we finish up the class. When we're looking at the topology for this class, it's mainly just going to be 10 routers. 10 routers without switches. So if we look at specifically the diagram that I'm mainly going to be using, it is going to look like this. Okay, so it's the same one that's used for the technology labs. So I'm not going to be going through the exact same examples that are in the technology labs, but it's going to use the same topology. So if you want to load the initial configs up for this, it's going to be very straightforward to do. And pretty much any topic variation that we need to do, we'll be able to do it in this particular topology. Where can I find the logical topology for the ATC? I'll be posting this before we start the actual class sessions next Tuesday, but it's the same logical diagram that's part of the workbook in the Advanced Technology Labs. So right now, if you already have access to the workbook, then just log into the member site, go to the workbook page, and then on that first intro page, it should be, actually, I don't know if it's the first intro page. Let me take a look real quick. It should be under, let me go back to members. Members, then under workbooks and under V5 workbook for routing and switching. Then the section is the initial configs and diagrams right here. So you'll see this is what the logical physical topology now looks like. This is the network diagram that we'll be using. And then, of course, we'll be varying the protocols that we're using for it, but it makes it a little bit easier that just there's one template of initial configs you can use to follow along with any of the examples that I have. So if you rent the racks, or even if you use your own equipment, we post the initial configs anyways, so you'll be able to quickly load these up take a snapshot of those configs, and then it's easy to roll back between them and switch between configs in order to change between sections. But that specifically I'm going to talk about later once we go through actually starting with the technology topics. There's a question, would it be possible to provide a list of servers that we can purchase for support, also a document describing the key points of installing the CSR instances? This, honestly, I cannot do because there's too many variations in the physical server world in order to say that this is kind of the spec that we're going to stamp and say it's a good one to use. Instead, what you can do is just go to our online community, which is ieoc.com. And there's a number of people that have already been talking about how to build the hardware spec. So under CCI forums, and then under the section that is Cisco hardware, I created a couple different threads here that were how to, this is the original one here, the equipment build. The problem is that this thread got too long. It's got 500 responses to it. So if you look at the other ones, these are more specific as to how you would build it in one option versus another. So if you have questions on a physical server, just post it here under this section for CSR 1000V, and then other people will tell you, you know, I bought this Dell server, or I bought this HP server, and it worked, and you can get a kind of an idea of what they're using. The reason why that I can't really give you a good recommendation is that the hardware that we're using is far overshooting what you would need for one topology. So in my case, our boxes have like half a terabyte of RAM, which is going to be way overkill for running one individual topology. But how much memory is the other question. How much memory do you need per instance? You need about 2.5 gigs of RAM per instance, but you don't necessarily have to have that dedicated, because depending on what your hypervisor is, you can oversubscribe the RAM. So let's say maybe you had 16 gig, and that means you're only supposed to be able to boot about 8 instances. You probably could get somewhere closer to maybe 10 or 15 with that. Because depending on what particular hypervisor you're using, you can swap the memory to disk. And the disk I/O for the CSRs is basically none, because you're not actually routing any traffic. So just running the control plane is not very intensive for the box to do. And the only thing is that if you have low specs of hardware, it takes them a long time to boot. So once you get them to boot once, then it's fine, because you can just snapshot the config. With INE using regular 3560s with 15.0, do you know what features the INE labs would not work on regular 3750s with 15.0? So in terms of the switch code, as far as I have seen, there's only one feature that's not supported in the non-X version, which is IPv6 first hop security. So for those particular topics, I'll be demoing those on 3750Xs, but you don't need the X switches for the other topics. So basic spanning tree, VTP, trunking, ether channel, that type of stuff is going to be supported basically on any switch platform, regardless of what the version of it is. So you don't really need the X switches. If you want to support 100% of the features, then yes, you would need them. But if I was personally doing a blab build, I would not buy the X switches. I would buy just the regular cheap ones, and then run either 12.2S. You don't need 15. So either run 12.2SE or run 15.0SE, and that's going to be the vast majority of features that you would need there. There's a question, will it be possible to rent just the switches? Actually, yes, it will be. So we're going to be posting multiple variations of this topology. So you basically will be able to choose, what do I need to do for this specific lab? So if you want to rent just 4 switches, that's going to be cheaper in terms of tokens versus renting 10 routers plus 4 switches, or renting 20 router instances and 4 switches. Because basically our cost is no longer fixed with it. It's a cost based on utilization. So the more instances that you are using at a given time, the more the token cost is going to be. But the advantage of it is that you get to choose what specifically you want, and then you can focus like just on layer 2 switching. There's a question, is iOS 15.3M a good substitute for 15.3T? it's going to be pretty close. It's not going to have all of the features, but it's going to be pretty close as to what you need to do. One of the things that you can actually do here to figure out what is supported and what is not supported is to do this. And I'm going to show this in more detail in our next sections here. But let's say that we go to, let's go to the main documentation page. Cisco's documentation I'm talking about here. And let's go to a particular release. Let's say products iOS, regular iOS, 15 M&T, 15.3 M&T, and 15.3.3M. Okay, eventually it should redirect you to a basically collapsed documentation page where most of these are going to be talking about the same releases. And what you'll see on the web page here is a little bit different depending on what release you're going to. But if you go to the release notes and go to the cross-platform release notes, there is something that is really important that you'll need to read through here as you're going through your normal preparation. And again, I'll talk about this in more detail when we talk about specific preparation resources. But there's a section of the documentation here that is what are the new features and the important changes. So if you've already been using iOS, let's say you've been in networking for the past 10 years and you've already used a lot of the core iOS features, you may not need to learn how does static routing work, how does RIP version 2 work. Okay, you might already know this from your previous experience, but at the same time you might not know what are all the new advances and what are all the new features. And that's where the release notes can help you. So what I would do personally is start at release 15.0, go to these release notes, go to the new features, and it tells you in each specific sub-release, go to the software features and think about, is this going to be relevant to routing and switching or not? Okay, BGP add path, yes, would be relevant. Cube serviceability, no, that's going to be something for voice. Okay, HSRP aware PIM, maybe, for multicast routing. EIGRP IPv6 MIBs, probably not, because we're not really dealing with network management a lot. But the thing is that if you go through these documents step by step, and if you click on the features, it takes you to that section that explains what is BGP add path or what is BGP route server, for example. And then you want to read through the topics just so you know that this feature is available. This is what it does. Try it out once or twice. And then if you need to reference it in the exam, you know now where it's documented in the doc CD. So you don't need to memorize all of this, and I'm going to go through this in much more detail as we go through the documentation and talk about some of these minor features. A lot of the general logic of CCIE is that you don't want to have to memorize everything. You want to know how the core features work, and you want to know where can I reference the rest of the difference, because it's too many minor details to try to memorize. So as long as I know, what is add path and what is the design that it solves, you could always go to the document, copy their example, paste it in, change it around in Notepad, whatever you need, and then you have a functional working config. Okay, we'll see one of the big things that is true for is DMVPN. You do not need to memorize the DMVPN config. The config guide for DMVPN has a perfect template that you can take and almost copy and paste verbatim, and then it's gonna work. So we'll see, like I said, as we get into more details, where to specifically find these. But since we're talking about hardware and different software releases, if you're worried about your release not supporting a particular feature, you need to figure out what releases support what. Okay, you're supposed to be able to go to the Feature Navigator to do this, but most of the time Feature Navigator is wrong. So I shouldn't say it's wrong, it's not 100% accurate, which makes it more difficult for us if we're trying to compare two releases side by side. It's just that there's so many features in iOS, it's nearly impossible for them to get 100% accurate or even close to that for the Feature Navigator. So you'll be better off trying to manually go through the new release feature documentation, maybe put it out in a big spreadsheet and then just check the items off as you're going through it so you know what have I covered, what have I not covered, where do I need to go from here. There's a question about the workbooks, and I'm going to come back to this in more detail later. The question is, now in V5 we only have one workbook which includes all the advanced technologies and full-scale labs. Does the full-scale labs use a different topology? They use a different logical topology, but not a different physical topology. So the topology changes now based on the initial configs, because the topology basically is arbitrary now. So, and somebody else had actually a question to this, and let me actually show you guys real quick how we have it set up, or at least how I have one of my dev racks set up for this. Okay, so this is one of my development boxes for running ESX, for running VMware. And you can see it takes a minute to load, but here are the actual instances that it's running. I think this box has about 100 instances booted right now. And it's using 260 gigs of RAM, but the CPU is almost idle, because the routers really aren't using the CPU because they're not forwarding traffic. It's only if you had this actually in the data plane in a production network would you need to worry about the CPU. But the other thing that people are confused about is how does the networking work for this? So how do the routers actually talk to each other? And it's actually a very simple thing that is under, this would be here under configuration, and then under networking, where we have what is considered to be a virtual switch. Now, I'm not sure if you guys can see this because it's, I can't zoom in on this. Let me try. Okay, this is the virtual switch inside of VMware. And basically what it's saying is that there is a physical uplink. Okay, so this is a physical NIC card that's on the server. And this is where basically the switches would attach. So switch 1 is plugged into this port physically. Okay, if you actually click on this little dialog, you would see the CDP information that says switch 1's a CDP neighbor. And the packets come in here, and they're coming in as .1Q tagged. And the vSwitch, the virtual switch, says when it comes in, all of these ports on the virtual switch are supporting all VLANs. Okay, this is what, in the ESX terminology, this is what they mean by a trunk. Okay, you're saying that it supports VLAN 4095, which is all VLANs. So this means that from a CDP point of view, router 1 and router 2 are directly CDP adjacent without having to send their traffic out to the physical world and then back in. So in other words, if you're working on a lab that's not using the switches, then you don't need that portion of the network. You can have just a few routers that are connected to the virtual switch. Then by configuring the different .1Q subinterfaces, that's going to control ultimately how they can communicate to each other. So it makes it very easy to change the topology around, because the only thing you need to do is just create a new subinterface, give it a new VLAN number, and then the routers are automatically connected. Okay, it doesn't work here like a normal Catalyst switch would, where you don't need to create the VLANs. It doesn't run spanning tree, doesn't run any other features basically, except to say when a packet comes in, just bridge it everywhere. And you'll see that all of the routers will receive each other's frames. And the reason why is, if we go back to the ESX config, that the vSwitch, you would want to set it to run in promiscuous mode, which you can see here. Okay, it says promiscuous mode to accept. This basically says the vSwitch is a hub. So it's not actually switching based on the MAC address. It's saying when a frame comes in, just send it everywhere. Send it to the virtual switch. Because the reason that you would want to do this, normally you don't do this in a real production design, but the reason that we want to do it here is that we're trying to capture the frames. So you'll see as one of the other machines that are in that virtual switch is a Windows box. This is what's running Wireshark. So ultimately, when you rent the topology from us, you will have access to different virtual machines that you can use for testing basic applications. So as we're going through the different topics, a lot of the things that are at the application level, I'll be looking at tests from the application level. So let's say multicast, for example. Okay, the easiest way to test multicast is actually generate UDP feeds from one virtual machine on one side of the network, send it to the other side of the network, and see if the feed can actually be received. Because the routers, again, they are production routers. They do support the data plane. So most of these type of tests, I'll show live examples of them from the application side. So like TFTP server, FTP server, web server, that type of stuff, where when you test it just from the router, it doesn't really give you the overall understanding of how does this application work end to end. Good morning and welcome everybody to INE's CCI Routing and Switching version 4 to version 5 Transitions Technologies class. My name is Brian McGann and I'm going to be the instructor for these sessions. So first, before we get into any of our technical details, I want to start with a basic introductory section to talk about what is going to be the scope of this class overall and then how we're going to split up the topics. So we'll start with just a basic introduction about how to use the classroom software, if you have any issues, who to talk to for support, that type of thing. And then we'll talk specifically about what is the exact topic scope that we're going to be going through. So as I mentioned, my name is Brian McGann. I'm one of the instructors here at INE. I've been a CCIE for over 10 years. Back in 2002 was when I got routing and switching. And I currently have 4 CCIEs and a CCDE. So hopefully this year and next year there's not going to be any more of those coming. But you can also see my email address there. If you have any questions after class, please feel free to get in touch with me if there's anything that I can help with. You can also find me on our online community, which is IEOC for INE's online community. And you can post any general questions or technical questions there as well. Now, the overall goal of this class is to familiarize yourself with the new topics that have been introduced into the new CCI Routing and Switching version 4 blueprint. So ideally, this class is going to be best suited for people that have already gone through a lot of the topics in the version 4 blueprint, because the vast majority of them, probably 90% or more, do carry over into the version 5 blueprint. So maybe you were studying for the past 6 months, then you weren't able to get a version 4 lab date, and now you're faced with the version 5 blueprint. So you could think of this as kind of a brief supplement to the version 4 Advanced Technologies class, which if you don't want to have to start all the way from scratch with the version 5 Advanced Technologies class, you just want to see what's the difference between the topics, that's basically what we're going to be covering here. Now, of course, there is going to be a separate technologies class for version 5, and the schedule for that is posted on our blog, blog.ine.com. It's starting, I believe, the Saturday after Cisco Live, which is going to be 2 weeks from today, I think. Maybe 3 weeks from today. I have to double check. But the version 5 ATC is coming up, so if you have an All Access Pass, of course, you can attend that. Or if you purchased the previous downloads of the version 4 ATC, then you'll be able to attend the live sessions for that as well. But again, main point of this class is that we're going to be covering the new topics and the differences or enhancements for the changes between version 4 and version 5. So specifically, we're going to be covering the theory of the topics, so anything new like DMVPN or IPsec VPNs. If you haven't used those before, don't worry. We're going to start with the basics of what is IPsec, why would you want to use it, and then of course we're going to get into the CLI examples. So I'm going to go through the configuration of how do you build tunnels, how do you build dynamic VPN, and so on and so forth, and then just as important, go through the verification and the troubleshooting. Because as we know within the scope of the CCI lab exams, since we have such a limited time frame in order to accomplish the lab goals, you need to be very efficient in how you verify that something's actually working. And if you have a problem, you need to know what are the exact steps you can go through in terms of show commands, in terms of debugs, and so on and so forth to troubleshoot the topics. Now, the agenda in general between the 2 days for this class, today we're going to be talking about mainly the changes between the versions. So we'll go over Cisco's blueprint in detail. We'll also talk about the hardware changes, which I know everyone is been asking a lot of questions about recently. So what is our new topology? How specifically are we going to be hosting this? And then also, how can you build it yourself? So I'm going to be spending a bunch of time on that today. Next week's class, we're going to go through technology enhancements, which are for topics that were previously there, but there's new features on them, like OSPF loop-free alternative or EIGRP multi-AF mode. So it's not something that's completely new. So I know what OSPF is, I know what EIGRP is, I just need to know what's this new particular feature that is available. So I wanted to separate it that way so that you weren't seeing a lot of very new topics, like maybe DMVPN or IPsec VPNs, and then also trying to fit in all the changes at the same time. Now, in detail, specifically in today's classes, or today's class, we're first going to start with what exactly are the changes. So what was added to the exam, what was removed from the exam, and then what was moved between the written and the lab. So there's some topics, for example, like Get VPN, that are newly introduced, but they're only newly introduced to the written exam. So we'll talk about this from a theory point of view. What is Get VPN? Why would you want to use it versus other VPN technologies? But we're not going to be looking at the actual configuration of it, because of course it's tested in the written, not the lab. For any of the new lab topics, we are going to be looking at examples for those, like DMVPN, OSPF LFA, so on and so forth. Then we're also going to talk about what's the new hardware spec. So how does this affect what I can do? Maybe I had a home lab that I had built before based on the version 4 spec, and now I'm continuing in my version 5 studies. What can I do with this? So we'll go over this in detail. What is the official new hardware specification? What is the software version specification, which is actually really the more important point? And then what is our spec going to be if you were to use like the workbooks, the videos, the rack rentals, and then also if you wanted to build this topology on your own, what type of options do you have either in physical type of build, like using physical routers and switches, or virtualization, using like GNS3 or CSR1000V. Then for new technologies, today we're going to start with embedded packet capture, or EPC, which we'll see is a pretty straightforward feature. It's basically used just to capture frames as they're coming in or going out the router's interface, and then you can export these as PCAP files, which we can then use in Wireshark in order to do packet analysis. So for a lot of these other sections, I'm going to be using embedded packet capture and showing specifically how traffic patterns of something like GRE over IPsec versus IPsec virtual tunnel interface versus DMVPN look different from a control plane and data plane point of view. And we'll see with a lot of the new platforms, they don't support debugging in the data plane anymore. So this means from a troubleshooting point of view, in RNS version 5, we're going to be spending a lot of time looking at packet captures. Because you can't see it on the CLI, you need some external application in order to actually look at it. So we'll start with that. And then we'll talk about some VPN theory, like what are the differences between layer 2 VPNs with MPLS, with either point-to-point pseudo-wires, which is called the anti-transport over MPLS, and point-to-multi-point pseudo-wires, which is called the virtual private LAN services, and then how these differ from other overlay technologies like IPsec or DMVPN, and then also group encrypted transport. Now, as I mentioned, not all of these topics are going to be on the lab exam. So specifically with the MPLS layer 2 VPNs and Get VPN, we're not going to go through the actual configuration. So we'll talk about them from a high level point of view. Why would you might choose this in your design? What can it do? What can it not do from a design point of view? Mainly this is when you're trying to figure out, okay, I need a VPN solution for this particular customer or this particular network. These are my requirements. Which of these type of solutions is going to fit into this particular design? Now for next week's class, the second day of class, this is where we're going to start to talk about more enhancements for technologies. Now in the case of layer 2, really not a lot has changed here. We'll look at one minor change, which is VLAN trunking protocol version 3, VTP v3. Beyond that, that's pretty much going to be the scope of layer 2 switching. Most of these changes come in to IGP routing. So we'll look at the new configuration format for EIGRP, which is called a multi-AF mode, or sometimes called EIGRP named mode, and then some of the other implications of the change from EIGRP's previous format to the new format. So things like changes in the metric calculation and how that affects the feasibility condition, new enhancements for authentication where we can do SHA-1 based authentication, or SHA, I think it's SHA-256 maybe. Then also in the case of EIGRP, we also have IPv6 VRF Lite. So this means that you can now use EIGRP as your CE customer edge to PE provider edge routing protocol if you have an MPLS layer 3 VPN and you're trying to run 6 VPE, which is IPv6 over an IPv4 MPLS transport. And we'll talk about that in more detail later, what exactly that means. But one of the limitations of this before was that if you already had EIGRP, both for IP version 4 and 6, and you bought MPLS service, you'd have to change your routing protocol for version 6. So in the newer versions, that is now supported as well. In the case of OSPF, there's some other minor enhancements. We'll talk about how authentication changes. There's a new algorithms we can use and a new configuration format for authentication in OSPF version 2. OSPF version 3 now also supports multi-AF mode, which is kind of an interesting feature that allows you to route not only IPv6, but also IPv4. So OSPF version 3 is now more similar to IS to IS in multi-topology mode, which means that you have one single control plane protocol that can carry the network layer reachability information for multiple address families. So this means from a migration point of view, if you want to run IPv6 and IPv4, you can do it with a single protocol. You can do it both with OSPF version 3. Then we have OSPF TTL security. This is a minor one that is already implemented in other protocols like BGP, but it is good to be aware that these new features are in there. Then we'll talk about some network convergence and optimization enhancements. First and foremost, bidirectional forwarding detection, or BFD. It used to be that BFD had very limited support based on the hardware, like it was supported on certain line cards of 7600 router or Catalyst 6500. Now BFD is pretty much supported everywhere. So we'll talk about within the scope of network convergence and reconvergence, what does BFD mean and why would you want to use it? And then we'll also look at some new enhancements for IGP convergence time, both in EHRP fast reroute and in OSPF fast reroute, where OSPF fast reroute is also called the loop-free alternative, or LFA. So we'll see specifically why you would want to use this, and then what features that OSPF kind of borrows from EHRP in the feasibility condition logic in order to get very fast sub-second convergence by using the loop-free alternative. Then last but not least, we're going to talk about some minor enhancements in network security. Mainly these are going to be focused on IP version 6, so changes with the IP version 6 router advertisement guard and DHCP guard and source guard. You'll see that this is very similar or very analogous to the IP version 4 counterparts, which are DHCP snooping, IP source guard, and dynamic ARP inspection. So it's basically the same type of logic. The implementation, of course, is different because the version 4 versus version 6 protocols are different. And we'll also see that there's some hardware limitations on which specific platforms that you can run this on. So only pretty much the newer Catalyst versions and the newer Catalyst hardware can actually run this feature. Okay, so before we get into then our next section, which is going to be specifically about the changes in the blueprint and the changes in the hardware. I saw we had a couple of questions here. If you have 3 switches that can support the new iOS and one that can't, what would be the limitations of being able to support the labs? Could I use just the one switch as a specific switch and still support most labs, or should I replace it? We are going to talk about this in the hardware section, which is actually coming next. So when you're looking at, if you want to build the topology and you're looking at using physical devices, what are the advantages and what are the shortcomings of choosing one platform over another? To tell you the truth, the switches don't really matter. You'll be able to do 99% of the topics on 12.2s, not on 15. So in the case of 15, there are enhancements, but most of them are outside of our scope, and most of them have to be hardware accelerated anyways, which means you wouldn't get them unless you're running it on the newest possible platforms like 3750X, 3850X, and so on. So we will talk about that next in the switching section, but the main thing with the topology is going to be the routers. It's not going to be the switches. You'll also see in the new topology design, we've essentially completely separated the layer 2 switching tasks from all of the other tasks in the advanced technologies labs, because you don't need to configure the switches in order to do OSPF routing or in order to do BGP routing. So for layer 2 LAN switching, you would be focusing on just LAN switching itself, things like trunking, VTP, spanning tree. You can do that completely outside of the regular topology, and then you really won't need to see it again until you start to combine everything back until the full-scale labs or to the troubleshooting labs. But when you're essentially just learning these topics, the switches really don't matter. You could just use ours at the end of the day once you go to the final troubleshooting or final full-scale labs, and you would be fine with that. There's a question, would it be possible to do a quick configuration demo on a GetVPN? Maybe. It depends on how much time we have. So I may come back to that later. We'll see how long we go today. It is kind of an involved config to explain all the different parts of it, but I will touch on it today, at least what is GetVPN. If you do want to see more about this, it is covered in our security classes. So if you look at the Security Version 4 Advanced Technologies class, I do talk about GetVPN and more specifics there. And then also there's lab material like technology labs and full-scale labs in security that cover GetVPN. But at least within the scope of routing and switching, it's mainly just for the written exam. I would assume that they would ask you, if you were to choose GetVPN versus DMVPN, why would you choose one versus the other? Or this is your topology, can it be supported? Is it not supported? So on and so forth. There's a question, do I expect that there is going to be a heavier IPv6 focus in the lab? Previously, you might need to know how to configure something relatively basic. Do you anticipate us needing to know how to configure more advanced features in IPv6? Probably yes, because they're trying to go a little bit closer to feature parity between IPv4 and IPv6. But really, if you understand routing, you understand routing regardless if it's v4 or v6. There's only minor syntax differences between the two protocols. We'll see now with things like eHRP multi-AF mode, now the syntax is the same basically between version 4 and its version 6 counterparts. Same thing is true with OSPF version 3. You could run OSPF version 3 and then do IPv4 routing with it or IPv6 routing with it. There's really nothing that changes from the upper layer point of view. It's just that you're running over a different layer 3 transport. So I would say yes. Everything that we test in version 4, you should also understand how to do that in version 6. But in general, it's just going to be minor syntax changes between the two of them. A couple other ones. Will you be going over not only how to do embedded packet capture, but also how to analyze the packet capture itself? Yes. So we're going to look at how do you configure the packet capture on the router, and then what do you do with it once you actually get the packets. Okay, you can look at it locally, but most of the time that's not going to help you because it shows you in the packet hex format, and I don't know how to decode the packet hex format because I'm not a network programmer. Okay, you're not really meant to look at it in that format. That's why Wireshark has the standardized format of the PCAP, and that's why the router can export it in that format. So we'll look at doing captures, doing export to a virtual machine that's running Wireshark, and then we'll actually look at that from the GUI point of view, especially, specifically what is inside of the packets. Now we'll see one of the feature differences between iOS with this and some other platforms like Nexus and NXOS is Nexus has Wireshark built in. So you can run the show to see it in the Wireshark format. Embedded packet capture with iOS does not have that. So you can do the capture, you can look at the raw capture, but you can't look at it in the Wireshark decoding. So you're going to have the external virtual machine to do that. So I would assume, probably within the scope of the exam, that they give you like screenshots of the packet captures and say, what's the issue that is related here? And that would probably be something in the new diagnostic section that is between the troubleshooting and the configuration section. Because unless they give you access to actual virtual machines running Wireshark, then you're not going to be able to do the packet capture yourself in either of those sections. Do we cover network analysis? I saw ERSPAN embedded packet capture. This is similar to using Wireshark. Yes, well, yeah, we will be doing that. I've seen a lot on IOU and IOL lately. Last time I checked, it wasn't publicly released. It's still not publicly released. So we'll talk about that in the next section. You technically can use IOU or IOL to build your lab, but there's no official release that Cisco puts out there. So if you do a little digging, you might be able to find the images, but it's not something that you just normally log in like with a support account and then download them from Cisco's website. There's another question, will INE provide any training material for the new diagnostic section of version 5? We will. It's not going to be immediately, like it won't be out next week, but we will also have topics that, or training material that does cover that type of change in the format. There's another question. It's my understanding that the V5 lab will run completely on Web IOL, Layer 2 and Layer 3. Won't anything that needs hardware acceleration not be tested in the lab? That's a real good question. We'll talk. Let me hold off on that question. We'll talk about that in our next section that goes over the actual changes. Okay, so let's go ahead and take a short break. Let's take about a 10-minute break. And then when we come back, we're going to get into our first section, which I mentioned is going to be what are the actual changes from the version 4 exam in the terms of the blueprint, and then also in terms of the hardware. So we will resume in about 10 minutes. In our next section, we're going to look at the VTP version 3 enhancements and see how this fixes some of the security problems that we talked about with version 1 and version 2, and then also some of the new enhancements in terms of advertising new types of information that helps to streamline the administration of the network. So specifically in this section, we're going to briefly talk about what those enhancements are and then mainly look at the configuration examples on the CLI. So the first enhancement, the main one, is going to be the security fix to the configuration revision problem that we talked about before, where the issue is that in VTP version 1 or version 2, if a client or a server is added to the topology and they have a higher configuration revision number than the current topology, they're going to overwrite the database with whatever information that they have locally. So even if that local information is no VLANs, essentially whoever has the highest revision number is going to win and then overwrite the rest of the topology. Now we'll see specifically the way that this is implemented in VTP version 3 is that there are new roles introduced into the network. As opposed to having just your server, client, and transparent, you now have a primary server and secondary server, where the primary server is in charge of actually making the changes. The secondary servers are just listening to the changes made by the primary server, but they're not able to actually make any updates. So from a practical implementation point of view, what you would normally do in a VTP v3 design is that you can have all of your devices run as VTP v3 servers or VTP v3 clients, and when you want to make a change, you would promote one device to the primary server, make the changes, and then demote them back to the secondary server. So this means that if someone accidentally pastes in a config change, like deleting a VLAN, it's not actually going to be allowed because that change is only allowed if you are in the primary server mode. Now we'll also see the other big advantage is that there's new types of advertisements. So we can now advertise extended VLANs, so ones that are above the 1005 range, so 1006 to 4094, and we can also advertise our private VLAN configurations. So what are the primary VLANs? What are the secondary VLANs? Are they community? Are they isolated? And then what is the actual association between them? So this makes the administration a little bit easier in terms of synchronizing end-to-end what a private VLAN config would look like. And the other big one is multiple spanning tree. That when we do an MST configuration, we specify what's the name, what's the revision, and then what is the VLAN to instance mappings. Previously, you had to make sure that that was synchronized everywhere manually. Otherwise, the switches would fall back to inter-region communication, and it's not going to run properly if we have some type of maybe traffic engineering design for multiple spanning tree. We would fall back to just basically a common internal spanning tree when we're doing inter-region support. And then last but not least, VTP now can also be disabled. So you can disable it globally completely, or you can disable it on a per link basis. So that type of problem that we saw before where we were running VTP pruning and it was going to a server which wasn't running VTP, we don't have that problem anymore because you can just go to the link level directly and simply say no VTP, and then it's going to disable the process. We'll also see one other change here is in authentication. When you define a password, you can define the password as a hidden password. So it's not as simple as you go to the CLI and say show VTP password, and it shows you what the actual value is. So let's go ahead and first up, before we get into the configuration, let's take a look at where you would find these new changes in the documentation. Because again, this is the type of thing that you don't necessarily need to know all of the details about, but you mainly need to know at least where would this be located if you needed to reference the actual syntax. So let's first start at Cisco's main page, and we're going to go to, from the main documentation page, we're going to go to products and to switches. Then LAN access switches, let's say 3750X, any of these platforms. Then under documentation to the configuration guides. Okay, let's say 15.0 to SE. Actually, no, let's say this one. Software configuration guide. And you'll see this is the same between the 3750 and the 3560. So this is the documentation I would recommend to look at, the newer format for the X switches as opposed to the regular ones. This is going to show the additional features like IPv6 first hop security, for example. So under here, we need to go down to configuring VTP. And you can see now it documents here the VTP version 3 changes. And then let's look at the configuring the VTP mode. And then this is going to be under configuring VTP. Where did it go here? Chose the password first. So for the password, you just say VTP password. The other option here is that it says hidden. You can see optionally hidden to ensure that the secret key generated from the password string is saved in the nvram vlan.dat file. You configure a takeover. If you configure a takeover by configuring a VTP primary server, you're prompted to re-enter the password. Basically, what this means is that once the network is set up and you want to make a change, so let's say you want to add a VLAN or you want to change the MST configuration. When you go to make the change and you go to promote yourself to the primary server role, it asks you to re-enter the password. So it's just another extra added layer of security there to make sure someone doesn't change your MST config, because something like that could definitely be catastrophic because it determines how you're calculating the tree for actually forwarding through the network. So this is one of the other security enhancements there. And when you say show VTP password, it's not going to show you the password, because that doesn't really make sense, that it just shows you the clear text version like in V1 and V2. Then for configuring the VTP version 3 primary server, this here is in exec mode. So this is not in global config, and we'll see what the difference is here. This is when you want to promote yourself to the primary server, and you see that there's two different roles that it asks you for. One is for VLANs and one is for MST. You can think of this kind of like how address families work in other layer 3 protocols like BGP, for example. We basically have one topology that's advertising the VLAN information, and then we have another topology that's advertising the multiple spanning tree information. And VTP is basically just the layer 2 carrier protocol that's used to advertise the payload, which is the VLAN information or the MST information. So basically their idea was to make the protocol more extensible so that you have these optional topologies that you can advertise once new protocols start to get implemented in the network. So again, this is where you would find the document if you needed to reference it, and it's just listed under just configuring VTP. It's one single document. So let's take a look at this on the command line then. So from the CLI, we have the same setup as before, where we have the trunk links that are going from switch 1 down to all of the other devices. And right now I've reverted the previous config, so we don't have any VLANs configured anymore. So let's look at, first off, on all of these switches, let's look at just the show VTP status. So right now they're running in transparent mode. The domain name is configured, domain name is INE. And so they're all running in transparent mode. And we can see the number of existing VLANs is 5. Those are just the default VLANs. So VLAN 1, and then 1002 to 1005. Okay, so first step is we need to change the VTP version. So in global config, we're just going to say VTP version 3. And now let's look at the show VTP status. Okay, notice the difference here is that now it separates the feature of VLAN from the feature of multiple spanning tree. The idea of this is that you could be the primary server for VLAN, but you could be a client for multiple spanning tree, or vice versa. You're transparent for VLANs, but you're the secondary server for multiple spanning trees. So they're unrelated topologies. It just happens to be that they're running over the same control plane, which is VTP version 3. Okay, additionally, it should tell us here who is the actual primary server. So it doesn't show right now because we're running in transparent mode. So let's say this next. Let's say that the VTP mode is going to be, let's say, client, and we're going to be in a client mode for both VLANs and for MST. Okay, unknown would be like new enhancements that they want to add later. Okay, let's say this on everybody. VTP mode client VLAN and VTP mode client MST. Okay, if we now look at the show VTP status, we see that both for feature VLAN and for feature multiple spanning tree, we are the client. But notice here what it says, the primary ID is 0. This is talking about the primary server. So essentially the primary server has to register to the other devices and say, hey, I'm the one that's actually going to make the updates. So when the updates come in, not only are we checking against the revision number, but now we're checking against the source. So only the primary server can make the updates, which gets around that problem with someone else adds to the topology with a higher revision number. They can't actually make changes unless their identifier matches with the primary server. So next we actually need to create a primary server. Let's say switch 4 is going to be the primary server. So we go to exec mode and we say VTP mode is, or actually in global config, first we have to say VTP mode is server for both VLAN and for MST. And you can separate these into two different boxes. In this case, I'm just going to show it for both of the configs on one of them. And if we show VTP status, okay, it says my mode is server for both of these, but notice here the primary ID is still 0. Because I'm not the primary server, I am a secondary server. So now in exec mode, I say VTP primary, and for what particular role. So I want to be primary for MST. So basically now it's going to go and search throughout the network and figure out, is someone else primary? If so, I cannot take that role away from them. You can only have one primary device at a time. So eventually it should figure this out and it should return shortly. It says no conflicting devices were found. So do you want to continue? Yes. Okay, next we're going to say the same thing but for the VLAN config. So we're checking the current topology to figure out, is there another switch that's already the primary server for the VLAN feature set, so for the VLAN topology. It should return back here and say no conflicting devices were found, so yes, we want to continue. Okay, now on all the devices, let's look at the show VTP status again. The difference now is if we look at the device identifier. So everybody has basically a local MAC address. That's the device ID. And we compare that against the primary ID. This is the device that we're allowed to receive the updates in from. So if we look at the rest of the boxes, switch 2 is not the primary ID. You can see it has 4A00. This one is 3D00. Likewise, switch 3 is not the primary. Switch 4 is. Okay, so switch 4 is the one that's allowed to make the updates. Okay, so let's say we make some updates. Let's do some basic VLAN changes. So in global config, VLAN 100 to 120. Okay, if we look at the other devices and look at the show VLAN brief, okay, there's nothing special about that. So just normal VLAN advertisements, just like we had in version 1 and version 2. The only difference is that we have to make these changes from the primary server. We cannot make them from the client, just like in V1 or V2, but we cannot make them from secondary servers as well. Now, this isn't really the advantage. The advantage is that we can do these other applications. So, for example, extended VLANs. We could say we want VLAN 3000 to 3010. And if we look at the other switches and look at the show VLAN brief, we can see now that they're learning the extended VLAN numbers. So we no longer have to be in transparent mode, because this is one of the main enhancements of VTP v3, that we can now synchronize all of the VLANs 1 through 4094. We don't have that restriction of going up to just 1001. Okay, the next would be for the private VLANs. So if we were to say, for example, that we have VLAN, let's say 4000, and this is the private VLAN primary, And we have VLAN 4001 is a private VLAN secondary. It is going to be a, let's say, a community. And its association is to, no, I think it's the other way around. Let's say private VLAN, let's say another one. VLAN 4002, private VLAN is isolated. And on VLAN 4000, we'll say the private VLAN association is to add 4001 and 4002. Okay, so if we show VLAN, private VLAN, this is basically saying that 4000 is the primary, so this is the main VLAN, and then these are the secondary ones, 4001, 4002. If we now look at the other boxes and show VLAN, private VLAN, we can see they're learning it. Okay, so this is the other main advantage. So not only can you advertise the extended VLANs, but now you can advertise the private VLAN associations. Now you still have to do the assignments. You need to go to the link and say this is in VLAN 4001 and its parent VLAN is 4000, but at least you don't have to just copy and paste the VLAN assignments everywhere. Okay, also once you're done with these changes, you would demote the box back to a secondary server so that no one can actually make any changes anymore to something like this. Okay, the other change again is going to be for multiple spanning tree. So if we go to global config, let's say that we're running, or we have the spanning tree MST configuration. We'll say that the spanning tree MST revision number is whatever 1. The name, we'll say this is MST-A. And the instance mappings, let's say instance 1 is VLANs 10 to 20, and instance 2 is VLANs 21 to 30. Okay, if we now look at the show spanning tree MST configuration, it tells us the switch is not yet running in MST mode. We're still running in per VLAN spanning tree or maybe rapid PVST, but we now know what are the mappings of the instances, so everything besides 10 to 30 is falling back to instance 0. And if we look at the other switches and look at the same thing for show spanning tree MST configuration, we can see that they're learning that. Now if we were to try to make a change on one of the clients, if we say spanning tree MST configuration, and let's say we create instance 3 with VLANs 31 to 40, says you can't do that because you're not the primary server for the MST database. Now previously the issue with this wasn't that if you make the MST change you're going to overwrite the other boxes. The issue is that you make the MST change and then you fall out of the region and then you have to recalculate spanning tree by collapsing everything to the common internal spanning tree instance, MST 0. And in a production design, it becomes difficult to add new instances because you have to figure out where are you going to start and then migrate it in. Because when you're doing the inter-region design, we'll talk about this a little bit later, but there's some issues with the root bridge placement. And if you do the migration from the wrong point of the network, you start to block links and then ultimately drop traffic. So the advantage here with VTB v3 is that you just push out the changes, and then once everyone is synchronized, then you have the new instances that you start to run the MST instances for. Okay, the other one, as I mentioned, would be the VTP password. So in a global config, if you say VTP password, let's say INE1234, and this is a hidden password. So let's say this on all of the other switches as well. Okay, we have the VTP password. If we now show VTP password, you see it doesn't show you the clear text version of it, which is good. And then let's say that we want to take switch 4 and we don't want it to be a server anymore. So we go to global config and we say the VTP mode is now client. And will be a client for both VLAN and will be a client for MST. Okay, so as I was saying here, right now, switch 4, it was previously the primary server, and now we reverted it to the client mode, both for MST and for the VLAN topologies. Okay, we also configured a hidden password on all of the devices. Next is we want to make a change. So someone is going to have to promote themselves to the primary server for whichever topology they want to make the change for. But the difference should now be, like let's say we do this on switch 1. We go to global config and we want to be the VTP server for, let's say, VLANs, or the VTP mode is server for VLANs. And if we say now we want to be the VTP primary for VLANs, now it asks us for the password. So if I remember what I set the password is, let's see if I can find it here. INE1234. So now we can see it's promoted. So again, the main point of this is that you're decoupling the role of the server and then who's actually making the updates. So once you want to make a change, you promote yourself temporarily, make the change, and then when you're done, you demote yourself to make sure that you don't accidentally overwrite something later, like you paste a config in and you paste it into the wrong box and then you delete all of your spanning tree instances. So the configuration overall is really not that much beyond the previous examples that we saw for VTP. And you can see this again just go to this document. I would recommend to read through the overview here of version 3. There's also another document that if you just search for VTP version 3, this was the original one from the Catalyst 6500, which was the first platform that they implemented it on, where this is a white paper on what were the overall changes. So this document is more about the high level things, not necessarily the config, but like what are the key benefits. The key benefits are that we have better administrative control over which device is allowed to update the other device's view. Okay, this is the main one because most people didn't run VTP because it was too scary that you make a misconfig on one box and you overwrite the entire network. So now they've decoupled those roles. That problem is now solved. But the other advantages are that you can now advertise the full range, so up to 4,095 VLANs can be advertised, that you can advertise the private VLAN info, and that you can advertise other topologies or other databases, for example, multiple spanning tree like we were just looking at. Can secondary servers create VLANs? No, they cannot. So if we were to go to another box, let's say that we go to global config, and we say VTP mode server for a VLAN, and now we try to create a VLAN, let's say VLAN 1234, it's not allowed because we're not the primary server. So when you say VTP mode server, this means that you are the secondary server. You would still have to go to exec mode and say VTP primary for what particular topology, either for MST or for VLANs. There's a question then what is the difference between clients and secondary servers? I think that the server writes the file to the flash versus the client. Let's see if it shows it in the running config. Let's see if we can show the file, vlan.dat. More flash vlan.dat. So you can't read it in clear text. That's a really good question. I'll have to look into that. I'm not 100% sure what the answer is, because effectively, if you're a server but you can't make changes, then you're effectively the same as a client anyways. So there should be no real functional difference between demoting them from primary server to client, and then if you want to make a change, promote them back to primary server, make the change, and then revert back. But I think that one document explain what the difference is. There's a question here, can a client be promoted to a primary server? No, it cannot. So you would have to change them to server, then promote them to primary server. So maybe that's the reason, that it just skips that one extra step, that you don't have to promote it to, change it to server first. Because on switch 2 here, if we were to look at the show VTP status, right now for MST we're a client. So if we were to say VTP primary for MST, it shouldn't allow us to do this. You can't be a primary server because you're not configured as a server to begin with. Oh, and also the other one that I mentioned, I forgot to show the config for it. You can turn VTP off now completely. So in global config, you can either say VTP mode off, which just turns it off completely, or you can go to the link level, like port 1, and just say no VTP. And that just disables it for that individual link. So if you don't want to use it, then you're better off just doing this. In the case of like Nexus, that's the same as saying no feature VTP. It's just turning it completely off. There's a question, how do you exit the primary server mode? Let's see, so switch 1 right now is the primary server. Let's see if we can say no VTP. VTP primary. Well, I know you could do it this way. You could say VTP client, VTP mode client, and then VTP mode server. Now if we show VTP status, well, it still shows our ID there. It still shows it for VLANs. But the thing is that this is not a saved config. So if the switch reboots, it loses its primary server status. So it's not like something that's written to the running config. There's another question here. Can rspan VLANs be advertised? I'm not 100% sure about that. Let's check that real quick. Let's say VLAN 2222 remote span. I'm not primary. Okay, so let's say VTP primary for VLANs. Then let's say VLAN 2222 remote span. And show VLAN, can we say show VLAN remote span. Let's check on the other switches. Yeah, you can. So it does advertise these other attributes. There's a question for the other features like BTP pruning working the same, it works the same way. So if the only other difference though with pruning is in the previous example that I showed, we had the link from the switch to the server that was a trunk, and the problem was unless you manually edited the allowed list, that broke pruning because the switch was sending the VTP messages to the server and then not getting a response back. The quick fix for that here would be just to say VTP off, or actually no VTP at the link level towards the server, and then you would never send the pruning requests to them. But otherwise, it's gonna behave the same for the VLANs, for the VLAN topology, because doing pruning for MST doesn't make any sense. So if you show VTP status under global here, we can see pruning is off right now. But you would set this on the primary server, and then the other devices would inherit it. And there's a question, is it possible to filter VTP packets based on a multicast address? Yes, you can. You can do that with a VLAN ACL, and you can do it with a MAC access list that's called from the VLAN ACL. Whether you can apply that on a per port basis or not, I'm not 100% sure, but I know you can do it with VLAN access list. So if you just wanted to stop it completely, you can do that, but it doesn't really make sense to do that because if you want to filter it out, you can just go to the link level and then say no VTP. There's a question, can a VTP client make an internal VLAN? That's a good question. It should be able to because the internal range should be reserved anyways. So let's say on switch 2, like interface fast Ethernet 10, switch port, no switch port, and show VLAN internal usage. Yeah, I can create an internal VLAN. This is a special case though because these are not advertised to any other devices. Like it says, it's just for internal usage. So if you were to actually go to, let's say we go to the server and say VLAN 1006, there's going to be a problem now when we go to actually create that. It says you can't create it because it's already being used internally. So this is the potential problem that I was talking about before. that if you have platforms that don't agree on what the internal range is, like Nexus starts at the upper 3000s into the 4000 range, but it also depends on what version and what platform of Nexus it is. So if you have mixed mode with Catalyst and Nexus, and then you go to create some VLAN on one switch that ends up to be internal on the other one, then you might have to end up renumbering on your servers based on this number not actually being allowed. So in the case of Nexus, when you show VLAN, what do you do? I think you say just VLAN question mark, and then it shows what number you can create, and it shows you what numbers are not valid for creation. But with Catalyst, you would say, like I talked about before, VLAN internal allocation policy, and I don't know why this platform doesn't support it, but some of them support the descending policy, which you would start at the upper end of the range and then count backwards. But if you figure there's not that many usages for the internal VLAN, so maybe cut 100 off of the top, and then say if I want to start numbering at towards the low end of the extended VLANs, maybe I'll start at 1100 as opposed to starting at 1006. So even if you start above that, I mean, there's not many cases where you realistically need 4000 VLANs to be created. But as long as you have the cross-section between them that they agree to not assign something that is internal, because otherwise, like you can see here, you end up in this error. The VLAN manager says you can't actually create it. Hello everybody, my name is Brian McGann. I'm one of the authors and instructors here at INE, and in this short video I'm going to be showing you how to use the configure replace feature in order to save yourself some time when switching between initial configs for your routers and switches. Now the config replace feature is essentially a feature that's relatively new in iOS that allows you to take a previously saved file and then replace the running config with that file. Now the reason that you might want to do this is that it's generally going to be much faster when you're trying to erase and reload your routers or your switches in order to get them back to a blank configuration, or when you want to switch between initial configs. So it's basically going to allow you to do a snapshot of the config and then quickly roll back to it. Now from a documentation point of view, this is listed under the Managing Configuration Files section under the iOS documentation, where specifically if we take a look at the documentation site, from the main Select Your Product website, we're going to go down to Products and then iOS. Regular iOS, iOS 15.3T. And then once this page redirects, we're going to go to the configuration guides, and then down towards the bottom under System Management, and then under Managing Configuration Files, and then finally to the Configuration Replace and Configuration Rollback. Now, I'm not going to go through the details of the individual document here, but as a reference, you may want to take a look at this later to see what are the other features that are available other than just what I'm showing here with the basic config replace. Now, the first step when you're dealing with your initial configs, of course, is to get the initial config files. So within the scope of our Routing and Switching version 5 workbook, on the member site, you're going to see this under the table of contents, under the workbook, under the RNS-V5 topology diagrams and initial configurations. So from this page, if you click on this resources button on the right here, under hardware configuration, the initial configs is basically a zip file that's going to have all of the initial configs that you would need to go through. So if you look in here, you'll see that there's a lot of different files, and if you're constantly erasing and reloading your boxes or your routers and switches, then it's going to take a lot of time in order to switch between them. So basically what you want to do is you want to take the initial config archive. So I'm going to open up my files here to the actual initial configs, and then I'm going to open up my terminal window. So specifically in this case, I have a rack rental session scheduled that is for Routing and Switching version 5. And you can see that to get into it, I'm just going to telnet to rax.ini.com, and then it shows here my particular username and password. So if I open up my terminal window, I'm telnetting there to rax.ini.com, just 23, and in this case it said that my username was rs5rack3 with this particular password. And then it's going to bring me to this menu that shows what are the particular routers that I want to connect to. So let's say, for example, we want to go to router 1. And when you see that the router's config is going to be blank, pretty much other than a host name. So if we just look at the show run output, we can see that there's pretty much nothing in there other than just the host name configured. So the first step that we may want to do here is take what's essentially the blank configuration on the router, and then we're going to write this to a file in Flash. And the reason why is that if at a later point we want to roll back to this blank configuration, we can quickly do that without having to use the control panel or without having to manually erase and reload the router. So to do this, it's very simple. We're just going to say that we want to copy the running config, and we're going to copy it to a file on Flash, and we'll call this our blank.config. So the actual naming convention doesn't matter. You can call it whatever you want. But if we now look at the file system, let's say dir star.cfg, we can see that we have that blank config file. Okay, next I'm going to pick some random initial config to load. So let's look at the initial config archive, and let's say maybe we're doing basic BGP routing. So under basic BGP routing, I'm going to grab router 1's config and just take this text file and just drop it on my terminal emulator. And I'm going to click on Send ASCII. This is basically the same as just opening up the file in Notepad or your text editor and then pasting it in. So if we now look at the show run output, we can see that there's a number of different changes. We have like a DMVPN network pre-configured here. We have some IP addresses pre-configured. But now what I'm also going to do is to copy this config to Flash, and I'm going to give it a new name. So let's say I'm going to call this simply the basic BGP routing. So we'll say copy the running config to Flash, and we'll call this the basic.bgp.routing.config. Now at this point, if we look at the file system, we can see that there's two different files in there now. If we dir star.cfg, and if I want to switch between them, instead of erasing the config and reloading, waiting for the router to take maybe 5-10 minutes or more in order to fully boot, and then pasting the config back in, what I can simply do is to say config replace. And what do I want to replace the running config with? I want to replace it with a file in Flash that's called blank.cfg. So it's going to say, do you actually want to do this? Because it's going to replace the entire config. In this case, yes. So it should take a minute, and what you should see ultimately is that it says that the rollback is done. Now if you see that it goes through a number of passes and then it says it has to abort for some reason, maybe there's some config that it wasn't able to roll back, you can manually go into global config and then remove whatever the errors are and then try to do the rollback again. But we can see now what the main difference is going to be. If we now look at the show run output, we should see that it's going to fall back to what our original initial config was. Now since I still have that other file in there, if we look at the dir star.cfg, I can now fall back to the basic BGP routing if I want to. We just need to say config replace on Flash to basic BGP routing.cfg. Do I want to roll it back? Yes, I do. Rollback is done. If we now look at the show run, we can see that that config is fully loaded there. So we can see this is just one of the methods where I'm taking the file and then basically just pasting it into the console. Another option here would be to take all the files completely and then either TFTP or FTP them to the router's Flash. You could extract the entire zip file onto Flash, and then you would just have to choose what's the particular directory and what's the particular device name in order to roll back to that initial config.
Hey everyone, Terry Vinson back with another portion of our discussion where we're going to start being able to focus on some of the technologies that we've only loosely discussed up to this point. Keep in mind, we explored exactly what took place when we ran OSPF in a non-broadcast multi-access environment. And the best example of a non-broadcast multi-access environment that we have in the confines of routing and switching version 5 is going to be the idea of a multi-point VPN configuration known as DMVPN. That stands for Dynamic Multi-Point Virtual Private Network. Now what we're going to see here is that we're going to use a typical arrangement of devices to create a topology to work with. So just like every other course that we've had, every other class that we've had, we're going to talk about everything from the very beginning all the way to the very end, and we're going to begin with the theoretical components. And there's no better way to start with a conversation about DMVPN when it comes to being able to illustrate what's happening. Because what we're now here is we're going to use a number of solutions that we've discussed up to this date. Now, what do I MGRE? That stands for multi-point GRE interface or GRE tunnel, so generic router encapsulation interface. Now, what this implies is that when inside of the concept of this virtual cloud that we have, what we're going to do is we're going to create a series of GRE tunnels. Those tunnels are going to extend across our service provider cloud to each of our individual devices. Now, it's through the creation of these tunnels that we're going to afford this idea of connectivity. And initially, in the very, very beginning of time when we set this type of thing up, we would use a series of point-to-point tunnels. Now, the issue is if I use a series of point-to-point tunnels and I were to come along and add, say, a fourth router, say R7 in this scenario, and connect it to this cloud, well, I would have to do configuration both here at the hub and here at this new spoke. Now, that is going to be an idea of how we resolve endpoints. So we have this interconnection of devices that are going up to the hub, but how does the hub know about the identity of the spokes without us going in and doing some specific configuration? And that's going to mean that we're going to need or employ a technology that we're going to have to become very familiar with in the confines of version 5, and that's going to be NHRP. That stands for Next Hop Resolution Protocol. Now, Next Hop Resolution Protocol is really similar in behavior to some of the other protocols that we've already talked about up to this point. For instance, we talked about the designated router in the context of OSPF. It's going to be a pseudo-node, a virtual device that sits inside of a device, could be hosted by multiple devices on an Ethernet segment in the context of OSPF, that allows that one unit or that one virtual entity to act as the centralized point of management for shared connections, thus restricting the amount of stateful entries we need to maintain in order to have communications in a broadcast environment. Now, keep in mind, I mentioned earlier that DMVPN is an NBMA. It's a non-broadcast multi-access environment, and we're going to have to understand how we can overcome certain hurdles. Now, in the confines of our EIGRP conversations and our OSPF discussions, we saw how we could take a pre-configured DMVPN environment and run our routing protocols on top of it. We skirted all of the details associated with DMVPNs until now. So what we're going to be doing is we're going to add the missing component to our understanding in order to be able to construct first of all, a very simple configuration. In fact, in the confines of the CCIE routing and switching version 5 exam, we only need to concern ourselves with single hub topologies. And we are also going to have to recognize that there are 3 operational phases to DMVPN. Let's look at those. Phase 1. Phase 1, quite simply put, is going to be where we create a connection like we have right here, where this device can communicate through the cloud up to the hub and go through the hub to reach us. We do not have the idea of spoke-to-spoke connectivity in the confines of a Phase 1 DMVPN employment. So that's the most important element there. A lot of people get this process confused. Phase 1 means I build a DMVPN environment where I have spoke-to-hub reachability. Any spoke-to-spoke configuration is going to have to go up to the hub and back down. Now, that's not very efficient. Why? Because when we look at this, what we're doing is we're creating a bottleneck right here. We're creating a bottleneck that can cause us significant problems when we start thinking about exactly how much traffic we're going to be placing to that hub. Meaning every traffic that's coming from a spoke to another spoke has to travel up to the hub and back down. So in other words, what we're doing is we're eating up a lot of our bandwidth. That's why we deployed this concept of Phase 2. Phase 2 DMVPN is a deployment whereby we get the capability of creating spoke-to-spoke connectivity through the deployment of dynamically generated multi-point GRE tunnels between the spokes. So not only is it from R4 to R5 and R5 to R6, we could even and would even have a connection to where R4 would be connected to R6. So in a Phase 2 environment, dynamically we can create the equivalent of a full mesh topology. Now, we're not talking about circuits or virtual private circuits or switch virtual circuits like we did in frame relay, but we can see the similarity with regard to behavior. And the fact that by tying all of these things together, we're creating a scenario whereby we can have devices that think that they are adjacent for the purposes of layer 3 communications, even though they're separated by a large service provider cloud. Now, the last phase in this process is considered to be Phase 3. Well, what is Phase 3? Well, many people want to tell us that a Phase 3 DMVPN deployment is going to be a deployment whereby we add security, IPsec. Well, in all honesty, that couldn't be the furthest from the truth. Because what's going to happen here is that we can put security in a Phase 1. We could put IP security or IPsec in Phase 2. In the confines of Phase 3 DMVPN deployments, all we're looking at is high availability, stressing that idea of HA. High availability translates to the fact that we can have multiple scenarios whereby we have these different types of interconnections. So in a situation whereby I have one hub, so let's say this is R1, this is R2, and we have a cloud connecting these devices, what would happen in a scenario where I had other hubs? So let's say we have R3 as a spoke, excuse me, not hubs, R4 as a spoke, R5 as a spoke. Now inside the confines of this cloud, we can create tunnels such that our individual devices can be connected. Now, the thing that we need to understand here is that also we've discussed in the confines of our conversations other protocols, things like VRRP, Virtual Router Redundancy Protocol, HSRP, Hot Standby Routing Protocol, even GLBP, Group Load Balancing Protocol. But for the confines of our conversations, let's focus on these two. Now, if we were to take these components and connect them on a shared network whereby one is going to be active and one is going to be standby using either VRRP or HSRP, we can create a scenario now where we have the capability of getting data off of this network segment or into this new network through either one of these two different devices. And the thing that we need to understand is that we have to recognize the fact that we can do that using the same individual physical connections, or what's referred to as the NBMA connection, that we have on all of the individual devices. So in this instance, it might be FA00. As we can see, we can create these dynamic and these these dynamic or static DMVPN connections, these tunnels on the same interface. So we need to worry about how do we make certain that the router delineates between one particular stream of traffic and another stream of traffic. These are all the things that we need to understand, and in order to be able to do that, we're going to have to move to the console in order to be able to leverage all of these interior and all of these individual capabilities in the context of DMVPN, dynamic virtual or dynamic multipoint virtual private networks. So what does it boil down to? Phase 1 is spoke to hub connectivity. Phase 2 is dynamic spoke-to-spoke connectivity, plus the existing connectivity that we had before. And Phase 3 DMVPN boils down to high availability scenarios where we can employ broader scopes with regard to routing protocols, where we can run first hop redundancy protocols, any tool that's going to allow us to enhance the functionality. Keeping in mind that we're able to do multiple DMVPN tunnels across individual physical interfaces. The NBMA connections is what we're going to refer to them. We're going to have a DMVPN connection and an NBMA connection. And we're going to also have to recognize the fact that our different routing protocols are going to behave differently. As a perfect example, if we go back to the original illustration, this physical interface, or these interfaces right here, in this drawing, are 3 independent tunnels. What we would end up actually having happen, and I'll go ahead and just erase this part right here, is that these 3 tunnels would actually, or these 3 virtual tunnels, would coalesce on one virtual interface, a tunnel interface. Let's say tunnel 0. And tunnel 0 would be a MGRE connection. So in the confines of phase 1, I have regular GRE tunnels on the spokes and a multi-point GRE on the hub. In phase 2, I'll go ahead and change pin colors to illustrate a phase 2 connection, I'm running MGRE all the way around. So there's MGRE configured under the individual link, the virtual or the tunnel interface that we configure on each of the hubs, and also, each of the spokes, and also on the hub. So keeping in mind the way all of this operates and interoperates depends on what our design model is. In order for me to get that concept of being able to send traffic directly from a spoke to another spoke without having to send the traffic to the hub, I need to have MGRE capability so that I can get that multi-GRE connection, multiple GRE tunnels on one logical tunnel interface. So in other words, all we're going to do is go into it and specify the particular type of tunnel as being GRE, and then it's going to be multi-point configuration. Now, the other thing that we have to understand here is that this is a dynamic process, and I mentioned that pseudo-node style configuration. The way I want you to think of it is this. If in the context of R2, think of the fact that I have a little server running here now. This server is referred to as an NHR server, a next hop resolution server. Now what will happen is that our individual spokes are going to be statically configured with the identity of the hub. They're going to hold where the HR server is. They're going to know that in order to participate in this multi-point GRE configuration that is DMVPN, they're going to register with the logical entity that exists on the hub. When they register, they're going to tell the hub who they are and what addresses that it would use to reach them. Now, once every device, R4, R5, and R6, has been added to this topology, what we're going to find is that the hub now knows all of the information, and it's going to communicate that information back down to each of the spokes, so that the spokes now will have the capability of being able to identify how to reach each other within the service provider cloud. It's going to be involving a series of dynamic or static mappings that we can utilize if we want to override the actual dynamic behavior. But if left alone, this process is beautifully simple and elegant in deployment and operation. So, and we're hoping that we'll be able to appreciate that once we start turning to the command line interface to see what's involved in making all of this happen.
Good morning, everybody, and welcome back to INE's CCIE Routing and Switching version 4 to version 5 Transition Technologies class. I am Brian McGann, and in this session we are going to be talking about the details of dynamic multi-point VPN, and then we're going to look at a bunch of configuration examples. Today's agenda, like I mentioned, we're mainly going to be focusing on dynamic multi-point VPN today. I'll spend some time talking about just the overall theory of DMVPN. What is it? What are its use cases? Why would you specifically want to use it? And then we'll talk about the configuration go through a bunch of examples on the command line, look at the configuration differences between DMVPN Phase 1, Phase 2, and Phase 3, and then most importantly, talk about how our Layer 3 routing protocols behave over DMVPN versus different types of other topologies. Now, this is probably the biggest change that we'll see in the routing and switching version 5 blueprint from version 4. As most of you hopefully already know, the big change was that frame relay was removed, and now we're using dynamic multipoint VPN in its place. So we'll see that a lot of the basic design functionality is kind of similar between the two protocols, because DMVPN basically is a hub and spoke type network, but it's a layer 3 overlay tunnel as opposed to being a layer 2 technology like frame relay hub and spoke or ATM hub and spoke is. But we'll see from a routing protocols point of view, like when we run OSPF over DMVPN or we run EIGRP over DMVPN, a lot of the same behaviors will carry over from our legacy frame relay to DMVPN. So if you understand how the basic routing logic worked for frame relay, then you're ahead of the game already for DMVPN. We'll see the details specifically of that today. So let's talk about then just a general overview of what is DMVPN and why you would want to use it versus other types of VPN solutions. Now, specifically, DMVPN is a layer 3 overlay tunnel. Now, from a logical point of view, we'll see that DMVPN behaves as a hub and spoke type topology, but also it's going to support direct spoke-to-spoke type of traffic patterns. So this is fundamentally different than some of the previous non-broadcast multi-access technologies like frame relay or ATM, where mainly it was up to the service provider in order to do provisioning that is going to determine what are the actual traffic patterns that would forward through the network. So for example, if we were to think about this from a basic visual point of view, the way that a frame relay network works was that, let's say we have 3 routers on the network. We have router 1, router 2, and router 3. And these have regular legacy analog, or not analog I should say, but legacy frame relay links. These could be something like T1, these could be something like DS3 or subrate links, and these connect to legacy frame relay switches. So physically in the network, there's going to be some sort of connection between these switches in the middle. And from a logical point of view, then, the result is that the network looks basically like this. So let's say that router 1 is the hub, for example. And the logical point of view is that there is a layer 2 connection between router 1 and router 2. There's a layer 2 connection between router 1 and router 3. And then from an IP routing point of view, all 3 of these routers would be on the same IP network. So for example, they're all in the subnet 10.0.0/24. From a configuration in the service provider's network, they would be doing a manual configuration of what we call the permanent virtual circuit, the PVC, or specifically in frame relay, it's called the data link connection identifier, the DLCI or the DELC. And what this does is it determines when traffic is received in from the customer edge router, so whatever is on the edge of the customer network, where do I actually send it inside of the service provider cloud? So essentially the frame is received in and it has a virtual circuit number like PVC 100, for example, and then the switches determine how am I going to forward it in the core of the network based on that layer 2 header. So typically in most designs what you would see is that when you're provisioning frame relay or when you're provisioning ATM, that it's much cheaper to buy the network in a hub and spoke type topology because it minimizes the number of virtual circuits that the service provider has to provision. So technically you could do any type of topology you want. You could have frame relay full mesh, you could have ATM full mesh, you could have partial mesh like this hub and spoke, but most of the time it was more of a financial issue that when you're buying the circuits, it's very expensive to have the service provider provision them in a full meshed manner. So then from a logical point of view from the routing protocols, this limits what are the different designs that we can do for routing, and it also limits the scalability. So the issue becomes is that the hub of the network, like router 1 in this particular case, is essentially the aggregation point for all of the layer 3 routing adjacencies. So in other words, if I have 1,000 spokes on frame relay, I have 1,000 layer 3 routing adjacencies. And then from a data plane point of view, when I actually want to forward the traffic would have to go from the spokes, let's say from router 2, like we have a LAN segment here, A, and we're trying to reach a LAN segment B behind router 3, physically, when the traffic is moved through the network, it would have to go through the frame relay network out to router 1, and then router 1 would have to forward the traffic back out the same interface towards router 3. So of course, from a forwarding point of view, this means that the hub is going to be the bottleneck of the network. So if the spokes are connected with T1, for example, and the hub is connected with DS3 or T3, it means there's going to be a limit as to how many spokes that you can have without having very large oversubscription. So this was one of the classic design problems that you ran into with these type of networks, is that it's very hard to scale it because frame relay, first off, it only goes up to DS3, which is 45 megabits per second. And it's very difficult to build complex types of topologies, and it's very expensive to do that. So one of the kind of temporary solutions was to move to ATM, where ATM does support larger bandwidth. You can do OC3, which is 155 meg, or you could do OC12, for example. But really, you run into the same type of logical problem that it makes it very difficult to scale the network. Now, when we compare this to DMVPN, DMVPN is going to solve this because it allows us to have direct spoke-to-spoke traffic patterns. So even though when we build the network, it's going to be a logical hub and spoke network, when we actually go to forward the traffic, it doesn't necessarily have to go to the hub and then back down. Now, whether this is going to be the case really depends on what is the overall design and what DMVPN calls the phase of deployment. So specifically, we have 3 phases. We call them DMVPN phase 1, 2, and 3, aptly named. But what this is ultimately going to define, and we'll look at this in details today, is what are the supported routing designs over the network, and then ultimately what are the specific traffic patterns. So this is the big thing that we need to focus on is what is the result from a routing design point of view when we go to send IP version 4 or when we go to send IP version 6 packets over the DMVPN network. Now, as we start to get into more details of DMVPN behind the scenes, specifically the way the network works is that it's a combination of GRE tunnels and then the next hop resolution protocol, or NHRP. So specifically what this allows us to do is to have one tunnel interface from a configuration point of view, but we can have multiple tunnel destinations, which is why it's called a multi-point GRE or an MGRE tunnel as opposed to just a normal point-to-point tunnel. Now, typically, DMVPN also will imply encryption, that you run IPsec over the DMVPN tunnel, but it's not necessarily the case. So we'll look at in our examples today using DMVPN first without encryption, so we can see just what are the traffic patterns just dealing with the multi-point GRE and the next hop resolution. Once we get the basic design working, then we'll look at how do we do the crypto IPsec configuration over that, and then why would you want to do it from a real design point of view. Okay, but we'll see the big change. Excuse me. The big change and the big thing to understand about DMVPN is how the routing design works over it, because not all routing designs are going to be supported. Now, why would you want to use this versus other methods? The main reason why DMVPN is so largely deployed is that it's independent of the service provider's access method. So essentially this means is that you can buy any internet access you want, or any type of layer 3 solution. Doesn't necessarily have to be internet access, but as long as the endpoints of the network can get basic IP reachability to each other, they should be able to form the DMVPN topology. So you might have some sites that are on DSL, you might have some sites that are on GigE. As long as they have IP reachability to each other, it doesn't matter what the endpoints are. So this makes the design very flexible because you don't have to worry about buying layer 3 VPN service from the same provider in every site throughout the world. Or if you have multiple providers, maybe you have a provider for the US, you have a provider for Asia, and then from the reachability point of view, there's a problem because those providers have to do some interoperability. So in cases like MPLS Layer 3 VPN, generally the service offerings are much more limited versus something just like basic internet access, where I could have my cable modem at my house and I can join the DMVPN network that's hosted basically anywhere arbitrarily in the internet. Now we'll also see that another big advantage here excuse me, another big advantage is that the routing policy is not dictated by the service provider. So when we're dealing with MPLS Layer 3 VPN deployments, the service provider usually is the one that says you need to run a BGP or you need to run OSPF because that's all that I support. Now in the case of DMVPN, since it is an overlay technology, we can run whatever routing that we want. So this means that if your network is already running EHRP and you want to do a VPN deployment, you don't have to have EHRP redistributing into BGP at the edge. So you'll see that when you're actually going to provision or to buy MPLS Layer 3 VPN service, usually the providers are very strict as to what type of policy that they're going to allow. Because from a very large scalability point of view, usually they're going to say you can do BGP routing or you can do static routing. We're not going to offer you a lot of other options. The other issue too is that not all of the edge devices in the MPLS network are going to be Cisco routers. So if your enterprise network is already running EHRP and the service provider is using Juniper at the edge, well then it's not going to support that design. So it adds complexity in the routing design because then you have multiple administrative domains that you need to deal with. But again, in the case of DMVPN, since it's an overlay tunnel, you can run whatever routing that you want. But we'll see that there is still a requirement to have an underlay routing protocol. Could be something just as basic as static routing, like a default route to the internet, or in the case of maybe multiple sites, we could do BGP peering to the service providers. But ultimately, the internal routing domain is completely up to us. That we have very flexible design as to what are the protocols that we're going to use, and then what is going to be the end-to-end configuration for that. The other thing also is that DMVPN is very, very scalable. You can have potentially tens of thousands of devices, endpoints on the DMVPN network, but of course that's going to be dependent on the design, if it's a correct design or if it's a bad design. So when you look at some of the platforms, excuse me, some of the platforms that you could potentially use for DMVPN, this is one of the things that you need to think about. Is if I'm using, let's say, ASR1K as one of my hub routers, there's going to be some sort of upper limit onto the number of routing adjacencies that I can establish, the number of IPsec tunnels that I can establish, and that's going to be one of the issues with scaling the network. Is how big is the control plane of the device? Because in other cases, like MPLS Layer 3 VPN, you only have one Layer 3 routing peer, which is the service provider. But we'll see in the case of DMVPN, since it's an overlay, the hub is going to be the aggregation point for not only the data plane, if we're sending traffic from spoke to hub, but it's also going to be the aggregation point of the control plane. So not only might I have to have 1,000 EHRP neighbors, but I might have to have 1,000 IPsec tunnels, both from phase 1 and phase 2, and that can start to cause some problems in the platform's control plane from a scaling point of view. So what can you realistically support in the network depends on a lot of factors that we're going to talk about today, specifically with the DMVPN design. Now, the way that DMVPN works is we start to get a little bit more into the lower level details. As I mentioned, it's going to be a combination of multi-point GRE, the next hop resolution protocol, and then generally IPsec on the back end. So the overall goal of doing DMVPN from a configuration point of view is that the configuration is very minimal as compared to some other solutions. Like Layer 3 VPN, the configuration can get pretty involved. In the case of DMVPN, we have a very standard template that we would deploy on all the spoke routers in the network, and basically just change one field, which is going to be their IP address, and then they're all able to join the network. And so this means from a manageability point of view and an actual deployment point of view, DMVPN is a very simple configuration once you get the basic design set up. The other issue is that DMVPN allows you to technically do a full mesh of tunnels, but the tunnels are only going to be maintained based on the ones that you're actually using. So let's say, for example, that we have 1,000 sites in the DMVPN. If I want any-to-any connectivity between all of the sites, technically you're going to have the full mesh of tunnels. You have 999 tunnels on every endpoint. But in most real designs, you don't need a full mesh of connectivity. Your traffic patterns are probably going to be from the spoke to the hub, like to get to your main data center, or you might have minor spoke-to-spoke traffic patterns, but not all of the time. And that's one of the scaling enhancements of DMVPN, is that you can technically have a full mesh of tunnels, but you don't have to configure it manually this way. And also from the control plane point of view, the router doesn't always need to maintain all of the routing adjacencies and all of the crypto IPsec for these full mesh of tunnels. So we'll see specifically how this is going to work when we do the multi-point GRE config, and that how the tunnels are going to be formed on demand between the spokes based on either our phase 2 or phase 3 DMVPN deployment. Now there's a question here. If DMVPN requires only IP connectivity between the sites, what prevents all companies going 100% DMVPN instead of using frame relay, MPLS, ATM, etc.? That's one of the big design advantages. So if you go to DMVPN, you don't care about what the underlying transport is. Now, of course, the disadvantage here, though, is that it's a proprietary feature. So something like MPLS Layer 3 VPN, that'll run on any box. So as long as you can do routing, it's going to be supported. DMVPN is a Cisco-specific implementation, which means you have the vendor lock-in with your boxes. But if that's not an issue, then there's no reason really not to use DMVPN versus buying dedicated MPLS Layer 2 circuits or Layer 3 VPN. It just really depends on what are the overall traffic patterns and how large is the network that I'm trying to build. But that is one of the main advantages, is that you only need IP connectivity, and you can use then whatever you want to get there. So it could be regular internet access, could be dedicated circuits, but as long as the routers can reach each other, that's really all that we care about. Now, as we get into a little bit more detail, specifically the way that the tunnels are going to work is that there is a permanent tunnel that is formed from the spokes up to the hub that's going to be used to maintain the control plane of the network. So this is going to be the control plane from an IPsec point of view, assuming we're doing encryption. So we'll see that there's always going to be a tunnel that exists from the spokes to the hub, both for phase 1 and phase 2 IPsec. This is where our routing adjacencies are going to happen. So the spokes are layer 3 adjacent with OSPF or EHRP or BGP. But then the traffic patterns can be from spoke to hub, or they can be spoke to spoke depending on the underlying routing design. So we'll see from an actual configuration point of view, this means that we need 2 different routing protocols for IP version 4, and then 2 different routing protocols for IP version 6. We need our underlay network that is going to get us basic IP reachability to the from the spoke to the hub from their public addresses. And then we're going to need the overlay protocol that's actually going to run inside of the tunnel. So if we think of this from a visual point of view, basically what we would have is the DMVPN hub that has some sort of connectivity to the IP network. Okay, again, doesn't matter what this is. It could be gig E, could be 10 gig Metro E, whatever the link is. And then we have our spoke. So let's say we have spoke 1 and we have spoke 2. And again, their access method is arbitrary. So this could be DSL, could be cable, could be Metro Ethernet, doesn't really matter. Okay, as long as in the network in the middle, and most of the time this is going to be the internet, but technically it could be anything. You could run DMVPN over MPLS L3 VPN, you could run it over MPLS L2 VPN, but in most design cases, practically it's going to be running over the internet because it's cheaper access to buy that versus buying the dedicated circuits. So specifically, the first thing that we need to do is basically get IP connectivity from whatever address this is on the hub, so 1, 2, 3, 4, whatever their IP address is, and then this interface on the spokes, 5, 6, 7, 8. So as long as we can route between these 2 addresses, and we're going to be routing between these addresses by using our underlay routing protocol. So again, the underlay could be something as simple as a static route, like on the spokes we say IP route 000/0, and then point it to whatever the service provider router is. On the hub, maybe we're running BGP because maybe there's multiple hubs and we want some path diversity on how we can route into the network. But ultimately, first off, we need to have just basic reachability between everybody. So from a configuration point of view, this means your very first basic test is, can I ping from the spokes to the hub?